What is today? 22? Is that right? Attention. Yeah, 22. Okay, today is day 22. Yesterday we began section 2.8. Got about halfway through, a little bit more than halfway through, so the task today is to finish 2.8. We started looking at the derivative as a function, so we can start with some f of x and find the f prime of x. Not only does it describe the slope of the tangent at an individual point, and we could plug in that x value and actually generate the slope of that tangent line, we can also have now a function, some f prime of x function. If it makes you feel better to call it the g of x or the j of x or something else, that's fine. It's another function that has at each x value the calculated slope from the original curve, and we plot that slope as the y value. So instead of x comma f of x, it's x comma f prime of x. And we can continue to take higher order derivatives. In fact, we'll do some of that today and generate a second derivative function or a third derivative function or higher than that if need be. So we're keeping the x values the same. The y value becomes either the original function, its derivative, or the second derivative, or so on, as we generate these different pictures, these functions, these sets of points. Yesterday we talked about the definition of derivative that generates this function, this limiting process, and we're all kind of getting a little weary of that process, and it means it's about time to opt away from that process to some shortcuts, so I'm ready to. If we want to talk about where on a function we can find the derivative, then we want to know where that function is differentiable. So that word differentiable means it has a derivative. So that brings us to this point in section 2.8. A function f is differentiable at a if f prime at a exists. So if the derivative exists at an individual x value, it is said to be differentiable there. The derivative exists. Now there are several shapes of curves and several reasons why a curve will not be differentiable. And we'll take a look at those today. If it is differentiable on an open interval from a to b, that means it's differentiable basically at every number in that interval. So you really check differentiability just like you check continuity at individual x values. And if it's differentiable on a whole interval, it means it's differentiable at every value in that interval. So differentiable means it has a derivative. You can find its derivative. Let me add this in and we'll do some more with this while this sheet is up here. If a function is differentiable, then it's continuous. So we know if it has a derivative that the original function is continuous at that point. Now we'll look at in a few minutes the converse of this. I know all of you are, many of you have told me that high school geometry was your favorite subject. So you looked at theorems and their converses and inverses and contrapositives and all that stuff. So we will consider the converse of this as a separate idea because it needs to be considered. What do you think that would be before we take a little temporary break here from this concept? What's the converse of this theorem? If f is differentiable at a, then f is continuous at a. Anybody remember what a converse is? Besides a pretty good brand of basketball shoe?
Is it just the opposite?
Okay.
You're talking anti-differentiable?
Would it be f is continuous to a if f is differentiable?
Okay. Just basically take the if and then statements and interchange them. Remember that? Those of you many of you that told me high school geometry was your favorite high school subject. It was mine to teach when I taught high school. So if we take the if and then statement and basically make the then statement the if statement and vice versa, then we have a completely different statement to consider. So if a function is continuous at a, does that mean that It's guaranteed to be differentiable. Well, just keep that in mind because we're going to go through some differentiability issues and pictures, and then we'll come back to that converse of this theorem and see if we think it's true. And we won't go the inverse and contrapositive route today, although it may come in handy later in this course. Let's take a function that's a pretty simple function, the absolute value function. This happens to be one that's in the book, but this is one of those classic ones that you begin with when you talk about this differentiability issue. And in fact, we can't take the derivative of absolute value. So there's our function, absolute value x. We all know what that looks like. It's that nice V-shaped graph, just so we keep the y values non-negative. So we know over here it looks like this, and over here it looks like this. So this by itself would be the line y equals x. So when x is positive, we want the y value to be positive, so the y value is the same as the x value. This line over here is the line y equals negative x. So we have to use the linear version of the definition of absolute value. And the definition of absolute value, I think we've written this when we were first talking about split domain functions in here, piecewise functions. We said that the absolute value is x itself if x is greater than or equal to 0. Does this ring a bell? We've done this, I think, in this class at least once. And it's the negative of x if x itself is negative. So that definition ought to be illustrated by this picture, that the absolute value is just the line y equals x if x is 0 or larger, and it's the line y equals the negative of x when we have negative x's, because we got to make sure that the y values are not negative. So, is this thing differentiable? At x equals 0. Does the derivative exist at x equals 0? Well, you really can't just examine the single value 0. You have to examine what's happening a little bit on either side of 0. So as we come in from the left of 0 and a little bit from the right of 0, we've got to be pretty much doing the same thing from both directions if this derivative is going to exist. Remember, the derivative is the slope of the tangent. At x equals 0. So we want to, can you picture that? Can you picture the tangent line at x equals 0 on this function? If you're having some difficulty picturing that, it's because there's a whole bunch of lines that could be tangent, right? At x equals 0. It's not like a curve where you can just kind of lay a straight edge up against the curve and there's really only one line that would be tangent at that point. There's a whole bunch of lines potentially tangent. So what we want to do then is look at the different definitions or descriptions of absolute value. Umair.
Isn't that the, like, line will be the slope itself?
We want the slope of that tangent line.
So isn't it going to be the same?
A little bit left and a little bit right, you're correct. So a little bit left of 0, what's the slope of that line? Negative 1. So he's on to the reason why this is not differentiable. And a little bit to the right of 0, what's the slope of that tangent line? It would be 1. So what he's saying is you really can't be tangent to the line without coinciding with the line. That's correct. So a little bit left, it's negative 1. A little bit to the right, it's positive 1. You see that it's not going to be differentiable at x equals 0 because we're not approaching the same number from both sides of 0. So what we want then for absolute value of x, we really want to look at y equals x if x is greater than or equal to 0. So as we come in from the right, we look at that one, that definition or description of absolute value. I don't think we need to go through the definition of derivative. I'll write it out just for review purposes, because this is what we did yesterday. So we could do that on this line, y equals x, but we all know that the slope of the line y equals x is 1, right? So as we come in from the right of 0, it looks like the slope is 1. Now if we look at the other definition or description of absolute value, so when the x's we put into the absolute value function are negative, we have to negate them to make them positive. So it's y equals the negative of x. So I won't write down the definition of derivative again, but we all know the slope of y equals negative 1x is always negative 1. So if this is from the right, we're working on 0 over here from the right, and over here we're working on 0 from the left. Shouldn't we be approaching the same number from both sides if in fact it's going to have a derivative at 0? We should. So the derivative at 0 does not exist because it's not the same. The left-hand version and the right-hand version are not the same. So it's not differentiable at x equals 0.
Exist though?
Yes, it does. The function does.
But it's,
Because the point is plotted 0, 0, but does the derivative exist there? No, it doesn't. And this is kind of what I said earlier, kind of one of the classic ones to look at, because we all know what this graph looks like, and it has a pretty abrupt change in direction at x equals 0. It has a corner, okay? Or if you want to call it a cusp, that kind of quick change in direction. What's nice about polynomials is they have smooth changes in direction. So what's happening here at this point is this very much the same as what was happening a little bit to the left of there and a little bit to the right of there. So as we close in from both directions, it's the same as you come in from either side. This one clearly is not. It's very different as you come into 0 from both sides of 0. So here's a kind of a simple, I think, picture, an easy first example for a function that is clearly there. I mean, the point is plotted, but it's not differentiable at x equals 0. So the derivative at 0 does not exist. Yes?
So that function is still continuous though, isn't it?
Okay, so now we're getting back to that. Keep that in your hip pocket here. That converse idea. Remember, the converse of that theorem we looked at earlier was if it's continuous, then it's differentiable. What do you think about that now? This is continuous, but it's not differentiable, right? So it appears just from one test case that continuity does not guarantee differentiability. But according to the theorem, does differentiability guarantee continuity? Yes. So they're two completely separate ideas. One is true, the one that I had up here earlier. Differentiability guarantees continuity, but continuity, here's a prime example, does not guarantee differentiability. Now there are some pictures in your text about when functions are differentiable and when they're not. We've seen that corner. So other graphs that do something like this, at that point right there, it's not differentiable. Now can you kind of visualize trying to put the slope of the tangent line at that point? It's kind of difficult, isn't it? How do you lay the tangent line in there so that it's the same tangent as is coming from the left as is coming from the right? I mean, I don't know how to do it either. So, and there's another one, by the way, that's continuous but not differentiable. So it's not differentiable at this point. So the first derivative at A, when you have a corner or a cusp or any kind of abrupt change in direction, does not exist. Okay, this kind of situation, the derivative at this value does not exist. A point is plotted there, but it's not like we can come in from the left side and the right side of that point because we're at different places on the curve. Here's another way a derivative can fail to exist. We have a vertical asymptote, and the curve does this and this on either side of that vertical asymptote. Certainly, there's no point plotted there. We're going to have a hard time describing what the slope of the tangent is at that specific value. In fact, let's do a little bit more with this. As we come in from the left, what's happening to the slopes of these lines which are tangent? They're increasing and getting very steep, right? Some large positive number. What kind of a, do you think eventually they're getting practically vertical?
Mm-hmm.
What's the slope of a vertical line?
Undefined.
Undefined, right? So that seems to fit, right? And as we come in from this side, it seems like they're also nearing vertical tangent lines. So this idea of vertical tangent lines is clearly a problem for differentiability because the slopes of vertical lines are undefined. Now, could we have a situation, and this is somewhat repetitive, but it kind of picks up on that same issue of approaching vertical. You can actually, there are some pretty simple curves that do something like this, and then leave there fairly vertical and do something like this. At that point, that specific point that I have marked here, at x equals a, this derivative does not exist. Okay, and in fact, that's what this will be for this curve. Some of you have heard the term point of inflection, which Umair just said. That's what this will be. The curve exists there, but it is not differentiable there. Why? Well, look at what's happening from this side and from this side. Aren't the tangent lines getting more and more steep and nearly vertical? What's the slope of a vertical line? It's undefined. So if the tangent lines are vertical, remember the slope of a vertical line is undefined, and that's what we're dealing with derivative, the slope of the tangent line to the curve. So in all those situations, at those different a values on these pictures, the derivative does not exist. So let's, I guess, before we leave this sheet, reconsider that converse. If it's continuous, then it's differentiable. That is not true, right? Because this is clearly continuous, but not differentiable. This is clearly continuous, but not differentiable. So there's lots of counterexamples to that. But if it's differentiable, then it has to be continuous. Let's move into the second derivative. I think that's the next topic. And really any and all higher order derivatives. So third derivative, fourth derivative, seventh derivative, 11th derivative. So there are uses for these, believe it or not. We won't explore in this course really much beyond a third derivative. But when you get to Calc 2, 241, and you do some things called Taylor series and Maclaurin series, you'll need third, fifth, seventh, ninth, 11th derivatives to do some types of these series. So in general, higher order derivatives. So you can, I mean, if I never said anything else or anybody else said anything about second derivatives, you know what they are. They're the derivative of the derivative. So we have this function that we start with. We take its derivative. We have a new function called f prime. Then we do the same process all over again. We treat that as our original function. We take its derivative. Well, that's the derivative of f prime, which is f double prime. So we can iterate this process as much as is necessary in the problem. So we can have higher order derivatives. Now usually when you write the third derivative, you continue with this marking, but when you go beyond that, it gets a little ridiculous, so you put a little superscripted 4 or 5 or 6 or 11, because you just kind of be a little ridiculous to make all those marks. So if you see a little superscripted 4, that's fourth derivative, or superscripted 7, that's in parentheses, that's seventh derivative. That's some of the notation. If you use this notation for first derivative, then the second derivative using that notation looks like that. So it's the second derivative of y with respect to x both times. That's kind of the way I've remembered it. Or the third derivative of y with respect to x all 3 times. And so on. So there are some varieties of ways of writing second derivative or any other higher order derivative, but it's pretty much in line with what we've already looked at for the other notations. So by definition, if the first derivative is that, then the second derivative ought to be if it is indeed the same process, we ought to be able to iterate the same process with this new function, this f prime function, and do the same limiting, same definition procedure. So instead of using the original function, we're now using the derived function. And we'll do some of that, but most of the higher order derivatives, as far as us finding them, we'll either get off of a graph, which we'll do some of that today, or we're going to delay that a little bit till we get some of our shortcuts, and then we can find some algorithmic process to find higher order derivatives. One type of second derivative, third derivative situation we've already seen is a distance or height or position type function. We have said that if we took the derivative, we got the velocity, right? So the instantaneous rate of change of distance or height or position with respect to time is velocity. And then we also said if we took a derivative of that, instantaneous rate of change of velocity with respect to time is acceleration. So this ought to be s prime, right? And this then ought to be s double prime, which it is. So it's a second derivative. The authors also mention something in this little chain called the jerk. So if you think about an abrupt change in acceleration with respect to time, or just a change in acceleration with respect to time, think of, how do you change your acceleration? There's some kind of a jerking that takes place. So they refer to that, and that then would be the third derivative of our original position. Pardon?
No.
That's a J. I'm sorry.
Oh.
Or it looks kind of like a dotted Y. It's all right. Whatever you want to call it. It's the jerk function. So I've never really heard of it described like that. I mean, you can think of what a instantaneous rate of change of acceleration would be. I mean, that's not so difficult to think about, changing acceleration, but that's referred to in this book as a jerk function. So there is a use for these things, these derivatives. There are some interesting diagrams in your book, and I've enlarged some of these, and so we can analyze up here what's going on. So let's take a look at, if you want to look at this in your book, it is page 165. here on the same axis system, you'll see three functions. And let's not only just say, okay, that looks good, there's a line, and there's a parabola, and there's what looks like a cubic polynomial. But let's analyze and see if this stuff is in fact what it should be based on an original function, a derived function, and then the second derivative of the original function. So the original function is f here, which is the S-type curve. And if we take slopes of tangent lines on the f function, I would first of all want to know at this point, that's a key point because the slope there is 0. Is that correct? Now, if the slope is 0 there, shouldn't I be able to go to the derivative graph and plot the point y equals 0, right? Because on the original graph, we're plotting points in this fashion. On the derivative graph, we keep the same x value, but now instead of graphing the original y value, we graph the slope of the tangent line to the original curve at that x value. So here, the slope of the tangent is 0. That's why that point is plotted. Does that make sense? So we take points, we take slopes off of the f graph, and that generates points to be plotted on the f prime graph. Now I come over here. Where is the slope of the tangent 0? It looks like it's about right there. Shouldn't I then be plotting that point on the f prime graph? So do those two kind of make some sense? How else might we compare the f and the f prime to see if they're what they should be? We did a little bit of this yesterday. Okay, where the f prime is positive, what should the f graph be doing there?
Increasing.
Or vice versa. You take those same two ideas and transpose them. So here, in this region, the f graph is increasing. Is that correct? In fact, all the way to right here, to this point right here. So shouldn't the f prime graph be positive? Which it is, okay? That's why this graph is positive in this region, because the f graph, the original f graph, is increasing. Where else is the f graph increasing? Over here, right? The f graph is increasing. So that means that the f prime graph should be positive in that region, which it is. Is that okay? So we're kind of getting the feel of an original function and the derivative, what they look like pictured together. And what have we left out? Where the f graph is decreasing, which is right here. So in that region, then the f prime should be what? Negative, which it is. Is that all right with the f and the f prime? Okay, toss those two aside. Actually, let's not toss them both aside. Let's keep the f prime as our so-called original function. Now let's look at the f prime graph and try to come up with an f double prime graph in the same fashion we just did with f and f prime. So what would we want to look at? We'd want to look at where the f prime graph has a horizontal tangent line, right? Because now we're going to go on the f double prime graph. We're going to plot points in this fashion. So at the same x value, now we're going to take the slope of the tangent line, not from the original curve, but from the first derivative curve. That gives us our second derivative answer. Does that make sense? Is that too many derivatives all in the same sentence? So we look at the f prime graph here. The slope of the tangent line is 0. Shouldn't we then plot the point at 0 on the f double prime graph? What else can we look at? Decreasing and increasing. Well, where on the f prime graph, where is it decreasing? It looks like it's decreasing this whole time, right?
Right.
All the way to here?
Mm-hmm.
So if the f prime graph is decreasing, how should I then plot points on the f double prime graph?
Negative.
They should be negative. Good. So that's why this piece of the f double prime graph is negative. Now on the f prime graph, this part of the graph is increasing. What kind of points should I be plotting on the f double prime as a result?
Positive.
Positive. Okay, and that's why these points are positive. Is that okay, Umair?
So, the graph of f prime is a parabola. And,
Okay.
The f double prime is a straight line. Why is that?
You know what? It's amazing. I ought to pay you for my lead-ins to my next question. Not that I have any money to pay you, but if I had money, I'd pay you because that's a good segue. If you had to say what kind of curve f is, let's say it's a polynomial, what would you say that it would be?
X cubed.
X cubed. Does that look like pretty much an S curve? That's what X cubed graphs look like?
Mm-hmm.
Now, I'm not saying it is, but it certainly has that look, right? So let's say that f is an x cubed graph. Now, if we took the derivative, is it beginning to answer itself?
Yeah.
If we took the derivative of an x cubed polynomial, what should it be?
3x squared.
Okay, something x squared, right?
Mm-hmm.
In fact, I think we've done that. Didn't we do a definition of derivative problem yesterday? It was x cubed minus x, right? And the derivative was what, 3x squared minus 1?
Yeah.
Mm-hmm.
And then if you took the derivative of that,
X.
it would be something that had an x in it. So do you see, if it's a polynomial, do you see the degree getting knocked down one notch as you go? So if f is x cubed, then f prime ought to be x squared, which that is, parabolic, and f then ought to be linear, which it is. So that's a nice thing about polynomials, is you can kind of track the derivatives in terms of the degree of the polynomial.
If you went to the third derivative, would there be no more x? Or like, how could you keep going after
All right,
that?
well, let's do that.
If
I hadn't
you-
thought about doing that, but let's see, without cluttering too much. So if we were now using the f double prime to generate the f triple prime graph, what's the slope at every point? It's the same, isn't it? Isn't the slope here the same as the slope here and the same as the slope here? I don't know what this slope is. What's it look like?
3.
Maybe 3, 4, something like that. So if we were then plotting points on f triple prime, I need to pay you too. That's a good question. Why do you even need me here some days? I mean, you guys can just generate your own questions. You don't need me at all. So if we're plotting points here, so at the same x values, we're going to be plotting the slopes to generate the triple prime. Well, if the slope is always 3, at 1/3 we'd graph 3, at 2/3 we'd graph 3, at 1 we'd graph 3. Well, the y value is always going to be 3. What kind of a picture would that be? Horizontal line, right? So that's true. It would still be linear. Now, does that seem to fit what we wrote down right here? If we're dropping a degree each time, apparently if it were polynomial, then we'd go down to degree 0. Well, what's degree 0? Degree 0 is a constant, right? So we would expect that. Now let's go one step further. So now we've got the third derivative function, which is a horizontal line, whatever it is, 3 or 4, y equals 3, y equals 4. What would the derivatives on that be?
0.
They'd be 0 all the time. And wouldn't any other derivative higher than that also be 0? Right? Because once you get to a horizontal line, the slopes are 0 and they're stuck at 0. But we could go a little bit beyond this graph. That's good that you were able to make that leap. Any questions about this? Does that seem reasonable, how these are interrelated on the picture? Okay, there's another picture I want us to look at. And it has a distance, height, or position function. Actually, it's a position function. And I realize now that I made these the wrong way, but that's all right. We're only going to look at two of them at a time anyway. These are also in your text. I thought they were so good that we just had to talk about them. These are on page 166. The first graph is a position function, and we don't have a function. All we have are these points and these dots connected with this curve. So there's a position function of a car at times that are given out here to the right. Time 1, time 2, 3, 4, and 5. Now let's say we were generating our own velocity function. Velocity is derivative, right, on this. It's an instantaneous rate of change. So at x equals 0, I would come in here to this graph, and I've just brought this to use as a straight edge. So I know at 1 I'm going to be doing something like this. At a half, I'd be trying to get tangent to the curve. Well, at 0, being tangent to the curve, what is the slope of the tangent? It is 0. So in fact, that's how this point is plotted, right? It's the slope of the curve above it at the same x value. Now we go to x equals 1. So we'd come up here to x equals 1. I'd try to align this thing so that it's tangent at this exact point. So I'd align this, figure out the slope of that. Okay, how could we do that? Well, I know I'm going to clutter my diagram here, but since we're approximating, I could come out here and take this triangle that I have formed and figure out the slope based on the size of that triangle, right? And I want rise over run, so I want this distance divided by this distance, and that slope on the original position function curve is the point that I plot on the velocity curve. Now what is that? Well, without measuring that, let's come down here and say at 2, apparently what is the quotient of those two values? I'm sorry, we're at 1. Sorry. At 1, what does it look like we plot? 11 or 12, right? So the slope of that line, now it may not look like 11 or 12, but the scales are different. The scales on the y-axis are 20, and the scales on the x-axis are 1. So that could very easily be 11 or 12, right? Let's see how close we did. What would this be right here, from here to here? About 40? And what have I got here? 3? We're close, right? I mean, it was a very rough diagram on my part, but that's how that point is generated on S prime. That's what this is. This is S. This is S prime, which is velocity. And then we can continue to do that process. I'm going to clutter this diagram by doing this, but we could come up here on the curve to x equals 3, come in here with a tangent line to the curve, figure out the slope of that tangent line, and whatever the slope of that line is, that's what we plot down here at x equals 3, which it looks like it had slope, what, roughly 30? The slope of that last line that I drew is 30. So you take slopes off of the S, plot points on the V. How do you think we go from V to A? Same way, right? So if we have a velocity function and we want to plot points on an acceleration function, we can do this the same way. So we would take slopes, and there is a slope that's illustrated here, a slope of a line at x equals 2, and they've drawn that same triangle. This is 27, this is 3. So 27 divided by 3 at 2, we ought to be plotting 9. Is that okay? So we can take slopes off of the original and then plot points on the derivative. And we could do the same thing in going from acceleration to the jerk function. But this has just got the original 3. So does that seem then to work as far as the shape of the s function and the shape of the velocity function? As we go out here to the right, what happens to these slopes? They're increasing. Now, didn't they start at 0? Slopes were 0, and they continued to increase as we go? That seems to make sense, right? Seems to be the proper flow of how we go from one point to another. All right, what happens to these slopes? Look at this slope compared to this slope compared to this one. What happens? Are those slopes increasing as we go? No, they're decreasing, aren't they? So shouldn't they be larger when we start and then start to head down, right? Doesn't that acceleration curve shape make sense when we compare it to the velocity curve? The slopes are decreasing as we go. So the y values, which are the slopes, should be on their way down. So you always can compare, if you think about pulling slopes off one graph to graph the derivative of that graph.
How do you get the point 0 on the second derivative?
0, 15?
Mm-hmm.
Okay. Notice the difference between, and you probably can't. Let me get a new picture of this. I knew it was going to get cluttered, so I brought a couple. Let's look at the difference here. Do you see how this curve, as it comes down, begins to flatten out and do this? This curve?
Mm-hmm.
So as we get closer to 0, these tangent lines are getting flatter and flatter. This curve doesn't do that. So at 0, the slope of this tangent line right there is actually 15. Okay? So that's why this point gets plotted. So on this curve, if at 0 the slope is 15, that means at 0 I plot 15 on the other. So it doesn't quite lay down like the other curve. It doesn't come in and flatten out. It just is actually fairly steep and then just kind of stops. So it is true that the slope at 0 on this curve is 15. Therefore, we plot 0, 15 down here. Any other questions with any other interrelationships of these three functions? Now, when you continue out here to the right, if this graph continued in this fashion, can you see the slopes getting closer and closer to 0, right? And that's why these y values are getting closer and closer to 0. So as the curve flattens out, the derivatives get closer and closer to 0. And we'll see that happening a lot in the functions that we deal with and that we graph. Now, you're going to have some opportunity in the problem sets to do some of this type of comparison, where you look at three graphs all on the same axis system, and you decide which one is the derivative of the other and or the second derivative of the other. That was interesting. Well, somebody got a text message right here as we're speaking. Say, are you believing this idiot? You can believe what he's saying? I can't believe it. When's he going to shut up? Soon, actually. So tell him, soon. I think I gave you some problems from 2.8. How far did I give you?
24.
Down to 24. Okay? So let's pick up from that point. Page number. Starting on 167. So I gave you down to 24, so let's add these. 31, 37, 39, and 43. Now I want to see if I was any good today. Look at, on page 169, I didn't assign this problem. Page 169, problem number 36. Got 4 graphs. F, F prime, F double prime, and F triple prime. I want to make some quick stabs here as which is the original function.
Yeah,
D?
C. Yeah.
Or C, which one?
C.
Now D was given. Let's check it out. Okay, I'm not going to say what the answer is right now, and I don't know what the answer is. I'm going to check this out as you're checking it out. If I look at graph D, let's see if I can put that here. That'll make sense. We're looking at 36. If I look at graph D, I want to look first of all at where D changes direction. That changes direction here, so the derivative is 0. Is that correct? Now, if that's true, wouldn't then C be its derivative? Is that possible?
Can you repeat that?
Okay. I look at D. If that's my candidate for my original function, I'll look at where it changes direction because I know that's where the slope of the tangent is 0. So if it's 0 here, then the slope is the derivative, so the derivative graph should be 0. That would mean that C is that one. Is that okay?
Mm-hmm.
So that's at least a possibility that C is the derivative of D. Now, is D the original function? We still haven't made that determination. But I know now, I think, feel pretty comfortable with C being the derivative of D. Now, let's go then with C. C changes direction right here. What graph could be the derivative of C?
B.
B or A? Well, they're both 0 here, right? So let's go a little bit beyond that. Where C is decreasing, what should its derivative be doing? Should be negative, right? B? And where C is increasing, its derivative should be positive. Does that still fit in with B?
Yeah.
So it looks like if D is the original, C could be its derivative. And if starting with C, it looks like B could be its derivative. Now let's see if we can continue that process. It's kind of fun, isn't it? Now, so we're starting with B. What do I want to know? Well, at B, it's instantaneously flat right here. So is A 0 there? Yes. Let's look at where it's increasing, here, and also here, right? Isn't the whole graph increasing?
Yep.
So that means all of A should be positive, right? A is the third derivative. So what do we say? D is the original. C is the first derivative.
B is the second.
B is the second derivative, and A is the third derivative. Okay? All right, well, there's our additional 4 problems. That'll finish us from 2.8. Appreciate your attention.